So we now have some basic information about the things that affect population growth, births and deaths, birth rates and death rates. And we can estimate this information in the field, and that's really standard practice among a lot of population biologists. We may, in the case of lynx, mark a certain proportion of the population. We might radio collar some of those lynx. Over time, we might follow females and estimate how many are actually born each year and how many are recruited into the population, and that would give us a measure of birth rate. We might also estimate death rates by following the fate of those individuals that are actually wearing those radio devices or those that are actually marked. Once we have that information then, birth rates and death rates, we can then estimate our R value, our geometric rate of increase, and from that we can also estimate our lambda value, which is 1 plus R, or our finite rate of increase. So let's switch to another example. Let's talk about one of my favorite species and walk through the various steps involved in a PVA. Let's consider the case of the Ethiopian wolf. The Ethiopian wolf is really a very rare canid. It's an endangered canid that lives in the highlands of Ethiopia. There are only about 300 to 600 individuals left in the wild. They're very social. They live in packs or fairly large territorial groups. And they occupy a very narrow climate window, a very narrow climate envelope in the highlands, the Afro-Alpine zone of Ethiopia, at the tops of really these mountain ranges. So imagine we have a situation in which we're concerned with this population and we want to estimate in 20 years' time whether the current population will in fact persist. So we may ask, is there a 95% chance that this population will persist at 20 years' time in the future? So let's say we've gone out and we've studied this population, we've monitored it now for, I don't know, maybe 20 years previously. In order to carry out this analysis, this population viability analysis, we really have the first step being to estimate those birth and death rates. And we'd probably do that much like I mentioned with Iberian lynx. We might monitor that population by marking them and following their fates and recording births per individual. So that gives us some measure of birth and death rates, and that's really essential. When we have those values, the next step is to calculate lambda. So we have these values for our 20 years of monitoring data for each year, let's say. And from that, we would calculate our lambda values for each one of those years. So we'd have 20 lambda values based on those birth and death rates. When we have that information, we venture into the next step, which is really then to create an average or a mean lambda value. We hope that all of those values, those 20 years of data, encapsulate the variability that we might see in population growth rates. Again, growth rates are not static. They change from year to year. There might be a particularly warm year or a wet year that occasionally comes up. And we hope that across our 20 years that our lambda values that we've generated encapsulate that variability. So we create an average or a mean lambda value, and that's what we'll be using to project our population levels, our population size into the future. When we create a mean value, we oftentimes also estimate the variation, the variability in our data by calculating some measure of variance. A common measure is standard deviation, and this is a measure that you might be familiar with. It might be a cobweb from an old statistics course, but standard deviation is just some measure of how dispersed or how spread our data are around a particular mean. So standard deviation is often denoted with a big S, and as a refresher, let's quickly go through the calculation for standard deviation. So this is our standard deviation equation. So the standard deviation here for our sample is given the letter S. And the equation looks a little bit complicated, I have to say, but it's actually pretty straightforward. In the numerator here, we're taking each value, each one of our data points, subtracting it from the mean. So the mean here is given this little thing. It's an X with a hat, maybe a flat top on above it. And so we're taking each data point minus the mean and then squaring it. And we do that now for every single data point, and we sum all of those values. And when we sum those values, then we divide by this value, which is n minus 1, and the n here simply refers to the total number of data points that we have. And to make this more interesting, we end up taking the square root of this entire value to arrive back at our standard deviation. Make sense? Okay, so how do we interpret standard deviation? What the heck does standard deviation mean? Well, for normally distributed data, and normally distributed data would be data that follows sort of a bell-shaped curve, as you can see here. I've got on the bottom axis lambda values, and then on the y-axis here I've got frequency. So that's simply the number of data points that we have that are certain lambda values. So here, if this was, for example, 1, then this value would be the total number of data points that we have that are of value 1. Make sense? It's pretty straightforward. So let's say we do indeed have a mean value for our data as being 1. And let's say our standard deviation now is the value 0.25. So what we know about standard deviation is that if you add or subtract that standard deviation from the mean, plus or minus 1 standard deviation, we know that that data range will encapsulate about 68% of all of our data points. So if our mean here is 1, and we go out plus or minus 0.25, and the data in this range here are about 68% of all of our data points. What would we expect? This is 0.75, and this is 1.25 at this end. So that's basically 0.25 plus or minus our mean. So how about 2 standard deviations? If we went out plus minus 2 standard deviations, we find that a property here of standard deviation is that in that circumstance, the area under the curve would include about 95% of all of our data, all of our data points. So if we now went out 2 standard deviations, the area now under this curve represents 95% approximately of all of the data points that we've collected. So one thing to keep in mind is that standard deviation really represents a measure of the dispersion of data around a mean. So if we have a big standard deviation value relative to what our mean number is, then we might get a curve that looks something like this bell-shaped curve we have here. So we would have a wide spread of data around that mean. However, if we have a small standard deviation value, then our data are really concentrated much more around our mean. So they're less dispersed, less spread around that mean value. Make sense? So in our Ethiopian wolf example here, we've estimated a mean lambda and a standard deviation around that mean. And we hope that the data that fall within that spread encapsulate again all of the variability we would expect population growth rates to experience for this particular population of Ethiopian wolves. And that's really an assumption that we have to make. And one question really I think that needs to be asked is whether that's a fair assumption. Can we assume that we've captured all of that variation This is something we'll return to a little bit later, but think about that for a few moments. So the next step that we have is to estimate the population size at present. Remember, we need a starting point to project forward. So we want to estimate how many wolves are present. We know there are about 300 to 600 or so, as I mentioned before, but we do need a starting value. And population biologists do this sort of thing all the time. You can carry out simple counts of populations. You can also use sampling methods, more sophisticated modeling methods to get at a population estimate, a size estimate. And we won't cover that now, but there are a variety of different techniques that can be used. Once we have this starting point, then we project our population into the future. So we're concerned with what our population may be like at 20 years. So for each year, we will then randomly choose a growth rate from the spread of our data and apply it to the population we calculated for that year. Let me show you how that's done. So let's say our wolf population is 84, and we've estimated our lambda value to be 1.3 plus or minus a standard deviation of 0.4. So we can express these data, this information, perhaps graphically. And perhaps you remember this graph from earlier. We have lambda on the x-axis and frequency, or the number of values representing lambda, on the y-axis. So here's our mean value also here. And if we go out one standard deviation in either direction, plus and minus, we expect that approximately 68% of our data would fall within the bounds of that plus or minus one standard deviation. So we start with a population of 84. That's our starting population. We then randomly pluck a value from this distribution, and we use that as our lambda value that we will project our population forward with. So let's say we plucked a 0.9 value randomly from this distribution. We multiply that value by our population at present, and that gives us a new value. So 84 times 0.9 gives us a value of 76, if I've done the math correctly. So at year one, next year, we expect our population now to be 76, or we are projecting our population will be that value. So we can do that for year two now. We can do the same procedure. So in year one, we have a population of 76. We randomly pluck a lambda value from our distribution. Let's say it's 1.2. And we multiply our population times our lambda value to arrive at our new population estimate. And that, again, if I've done the math correctly, gives us a value of 91. So that's for year two. So we can plot these data. We can begin to plot them. So here's a graph that has year down on the x-axis and the population size, or the number of individuals, on the y-axis. So at point 0, at our starting point, we had 84 individuals. And as we start to project forward now, at year one we had what? We had a decline. We had about 76 individuals. And then at year two, we had what? We had 91 individuals. We basically carry the same procedure forward until we reach 20 years. So we might get the population behaving something like this, and at the end of 20 years we have the population, let's say, persisting. Now that we've done this for 20 years, our next step is to estimate the probability of persistence and the probability of extinction. So to do this, the first part here is to simulate our data. And we'd simulate our data many times. What do I mean by that? We would basically carry out the same procedure that I just covered. So we would estimate a mean and standard deviation around our lambda values, and we'd project our population through 20 years. We would carry that procedure out many times, so we would do that same thing, let's say 100 times. We could do more, we could do less, we could do 1,000, let's say, but 100 is probably a good starting point. So we do it 100 times, and as you can imagine, in some circumstances the population might do pretty well. We may have the population persisting. In other circumstances, we might have the population actually going extinct. There may be simulations in which we pluck out a series of negative values, and that results in the fate of the population being extinction. When we have this information, then, we simply summarize it in order to calculate the probability of persistence and extinction. So that's our final step. We look at our 100 simulations, all 100 here, and we add up how many times the population persisted and how many times the population did not persist or go extinct. How many simulations resulted in a persistent population? So we summarize those values up and we divide by the total number of simulations. So let's say in this case we had 85 cases in which there were individuals left over at the end of 20 years. If we had 85 out of 100, that basically gives us a probability of persistence of being 85%. What's the probability of extinction then? Well, it's basically 1 minus the probability of persistence. So in this case, that probability is 15%. So here we have our Ethiopian wolf population, and we know that there's basically an 85% chance that it will survive and be persistent at 20 years' time, or in 20 years' time. So is that reasonable? Is that a reasonable conclusion to arrive at? Does that mean that the population is in fact viable? It's really a judgment call in many ways, and I would say that population viability analyses oftentimes use a greater than 95% chance of persisting as being kind of the benchmark for which we assume the population is viable. But in this case, given the circumstances and situation for Ethiopian wolves, an 85% persistence might actually be just fine. Another twist on population viability analysis is that we might be able to simulate how different starting populations play out in terms of this probability of persistence or extinction. So with Ethiopian wolves, we know how many we've got, but what if we had half as many? What if an outbreak of rabies occurred and our starting population was considerably less? A good proportion of them died. Let's say half of them were remaining. We could then simulate how that translates in terms of probability of persistence. Similarly, we could say, all right, perhaps we reintroduce some wolves into the population. What effect would that have if we did it now on probability of persistence? So it's a nice, useful, and versatile tool for actually doing that. Now, we've run through the basic procedure for population viability analysis. I'm planning to hand you off here to my colleague Terry, who will build a spreadsheet that will do just what we've talked about. It will carry you through these basic procedures and arrive at probabilities of persistence and extinction.